2, 1. So a summary of all the derivative rules. When you begin calculus, you're going to be talking about the various derivative rules for functions. And there's quite a few of them, especially in the beginning. So this is kind of the summary of pretty much, one entire big chapter on derivatives. So here you see I have written out all the different possible kind of functions that you have. So function that is equal to a constant. So I just wrote it as c, so that's just simply a number. What if it's just equal to x? Okay, so it's just basically a line. What if it is some kind of a power function? So there's various now items with respect to these power functions. I have written out all of them. To be honest with you, just one of them is sufficient enough, but I think when students are starting, it's good to know and be comfortable when you have a power function, when it's just a regular kind of positive whole number that you have as an exponent, and then what happens if it's negative? Do things change? What happens if you're dealing with radicals, which is really just 1 over m. That's what you see there. And this continues. What happens if you have a general? So n over m. So where n and m is basically just some fraction, okay, in lowest terms. And what happens if it's negative? Once you kind of conquer those power functions and constant functions, you typically will move over to the rules for trying to do now taking a function and then multiplying it by a constant. So what's the derivative then? What if you have two functions now and you're adding them together? Because all the ones above here are just power functions or a constant. What if you start adding these things together? What if you start subtracting them? What if you start taking them and multiplying two functions together? What if you're going to be taking one function and dividing it by another? And then what if you take one function and treat it as an input to another function? So this last one is kind of the composition of functions, so composite functions. The one before it is quotient. So when you have division, then you have a product, okay, and then of course you have an addition and a subtraction, so a summation or a difference. All of these things can happen, and it's good to internalize all of these rules to the point where if you are taking calculus and you keep moving on, you should know these rules basically to the extent as you know your multiplication tables. That's how good the rules should be, so that if anybody gives you any example, you can right away internalize without even necessarily thinking about these particular types of rules. So let's break it down one by one, and then I'm going to apply it individually, okay, one by one to various examples. And each example is basically all the different rules. And then at the end, I'm going to challenge you. So I'm going to throw this ugly function at you, and let's see if we can take the derivative of that. This function applies every single rule that we have. And if you can do that, then you have come to the point where hopefully these derivative rules are going to become second nature. And when you conquer all of those, now you can start thinking, okay, I'm comfortable with the derivative. I know what it means. And now can I apply it to various applications, which you're going to see. All right, so let's get it kick-started. So here is kind of one by one all the different derivatives. So I'm going to, of course, the derivative would be written out in this way, or, sometimes you can write it out as dfx, okay, all over dx. This is exactly the same thing, just two different notations. So I'm going to just drop these notations, and I'm just going to give you what the rules state. So for the first one, so the derivative of any constant is always 0. Makes sense? Slope is 0 of a constant. It's a flat line. The second one, okay, so if you have an x, the slope is simply 1 of this function because it's a line that's crossing through 0 with a slope of 1. So the derivative is 1 everywhere. Now, as you move over to these power functions, so any power function that you have is always the actual exponent, which gets brought down in front of the variable, and then your exponent that you had originally, you're going to subtract 1 from that. That's what the derivative rule states. And now you apply this to basically all of these rules combined. So this, and this is just an extension of our exponent rule for power functions. They're all the same, no matter what. So for instance, within this one, doesn't matter how you write the function, if it's like this or if it's 1 over, they have exactly the same result. I like to always bring it back to here whenever I have a negative, just so that I remember. So that means the exponent comes in front, which is now negative n. You have your x, and then it's negative n minus 1. That's what you have as your actual exponent rule for this. So in terms of the derivative. Now, what happens if you're dealing with radicals? Radicals, I always encourage to write them back in as exponents that basically are just rational. So in terms of rational, meaning 1 over m, okay? So in this particular case, and the same thing applies. You take the exponent, you put it in front, so 1 over m, you multiply it by the variable, and then you take your exponent and then you subtract 1. How you massage these, so the actual exponent, how you write it out is up to you. But notice it's always the same thing. Take the exponent, put it in front, subtract 1. And you're just repeating this process over and over. The same thing here. As complicated as this radical looks like, it doesn't matter how you write it, these are all equivalent. They're all the same. I like to write them always with an exponent because I remember this particular rule very well. It's ingrained in me, so I change always everything with exponents if it's radicals. And then I can simply just take the exponent, put it in front, and then subtract 1 from the exponent. And I'm done. Now again, I can massage it, make it look better, whatever it is that you want to do, that's fine, but it's the actual rule that you must remember. And that's the same thing over here. So if it is negative, which really just means 1 over, this is just comes from exponent rules that we have, then just write it as an exponent and then again. So it's going to be negative n over m x minus n over m minus 1. And that summarizes all of these. Now, for any student, for any of these rules, if you really want to see why the derivatives are the way they are, I have proved all of them. So I'm going to put a link to the playlist of the entire calculus course. And if you go there, you can go through that playlist and you'll see that there's proofs. Proof of this, proof of that, proof. I have proved of all of these. Most of the time in grade 12 when you're beginning this, even in university, depending on what you're taking, most teachers or professors may not necessarily ask you about the proofs. I think it's a mistake. I think you should know where these things are coming from and you should have that skill, especially if you want to continue in mathematics, engineering, computer science, many of the STEM programs. So I encourage you to watch them, but of course you still have to internalize these so you know them like multiplication tables so that you can apply them whenever necessary. So now continuing on, so these are now actually no different. So now what happens is when you're studying calculus, of course, our functions don't just look like this. Now we start to integrate things together. We might take a function and we might multiply it by a constant in front. How does that change when we're doing the derivative? It doesn't. It just means that you have your constant which stays the same, and then you simply take the derivative of your function. That's all. That is the entire derivative. So that constant just will get pushed in front and take the derivative of that function. Now, what happens, okay, if you have a summation here? If you have two functions that are now added together, maybe two functions in terms of power functions. So now you're going to be creating polynomials maybe. Okay, so that's something. Even with radicals, you can do the same thing as you start adding them. How does this change? Again, it does not. The addition right here, luckily, just stays there, and then all you are concerned about is what is the derivative of the first function, and you're going to be adding it to the derivative of the second function. That is easy to remember, the addition. So that's just derivatives of both of them. And of course, I'm assuming that these derivatives are existing, right? So they actually exist, that they're not something that we can't take a derivative of. Now, in subtraction, the same thing applies. So it's exactly the same thing that we would have, except of course, now it's a difference between the two, but the rest remains the same. The difference of two functions, if you want its derivative, is just the difference of the individual derivatives that you have. Now, what happens when you have a product? Unfortunately, for a product, it's not as easy as just taking the derivatives of each. So this is a little bit more to try to remember, but it's not that bad, at least I hope. So with this, what this means, I'm going to just drop this x just so that it's easier for me to write it, and I'm running out of space there. So all you do is you take your first function and you take its derivative. You multiply it by the second function. You don't take the derivative there. Plus, you take now your first function and now you multiply it by the derivative of the second function. That is called the product rule for derivatives. Now, of course, these functions are with respect to x. I just dropped it there because I just wanted to fit it within here. But that's the product rule. So we have now completed quite a lot of them. This one is known as the quotient rule. So what happens when you have a function and then you're dividing it by another one? You can do it in one of two ways. You can bring the function from the denominator to the numerator by putting an exponent of -1 and then taking the product rule. Or you can use the quotient rule directly, which is very similar to the product rule, where what we're doing is we're taking our numerator, we're taking its derivative, we're multiplying it by the denominator, but now we're subtracting. So quotient is the subtraction. Product, notice that we had an addition. And now the rest, so this is going to be f1 repeated without taking the derivative, and then multiplied by the derivative of the second. So as you can see, the product rule and then the quotient rule so far looks the same, except there's a subtraction. So it's an easier way to remember. The only thing that you please don't forget, I certainly do at times, that you still have to take your second function, okay, put it in the denominator and square it. That is known as the quotient rule. It's probably one of the harder ones to remember. There's a little bit more to remember here than some of the other ones, but that is the quotient rule. And then the last one that you studied, most likely right in the beginning when you're taking on these derivatives, is when you have composite functions. Composite functions means that I always like to kind of do a drawing for this so that it's very visual, where we have an input coming in and that input is being fed into a function. So in here, I call this function f1 of x. Now that function is giving me an output, and then that output is being fed into another function. And then I have my result, which I call y, or in this case just fx, because that's what I've called them. But this is my now second function that I'm feeding it into. Put a little dot there because it is the output right here. Okay, that output which is being fed into the function so that we have our overall output. And that is the composition of two functions. And you can write it either like this, or you can write it like this with this little circle in between there. And notice that f2 is the one that comes first because f1 is the one that f1 of x is being fed into x2. So that's the composition. It's made up of 2. Now, what is the derivative here? So the derivative here is actually the derivative of your second function with your first function as the input to that derivative multiplied by the derivative of the first function. That is the overall derivative. So those are all the rules that we have. Let's try to apply them one by one to various examples. So these are all the different rules that we talked about. So here we go. If I wanted to take the derivative of this first one, the derivative here is just 0 because it's a constant. It's a flat line at -2. The second one, so this one is our power rule. So with the exponent, so if I wanted to take this, notice that this is with respect to t. So I've changed this, but it's still the same, so it's just a variable. So 3t to the 2. The exponent comes to the front, and then you're subtracting 1 from the exponent. So that's the derivative. Now, the third one, so this one, notice that for this, what I would do is, this is what I like to do, I would bring this back up to the numerator, so to make it negative. So this is what happens with negative exponents, right? So that's how these functions look like. So this one, which is g of y, so that's the derivative, would have been -4y, and then -4 minus 1 is -5. And again, you can rewrite this, if you like this, because that's what it actually will look like. And now notice we do have a problem in the denominator because y cannot be 0. It would not be differentiable there. It's just not continuous, right? So it would be undefined. So we have to be careful with this derivative, okay, at 0. Now, continuing on. So for this example, so the next example, I would write it out as x. Notice this is 1/3. This is the radical, but it's the third root of that. So now if I wanted to take the derivative of h with respect to x, this would have been nothing else but 1/3 x and 1/3 minus 1, which would have been -2/3. And now this one, if you would write it, it would be -1/3. And then here, this is starting to look a little odd. Okay, I'm going to rewrite it. So this is going to be 1 right there. This is what it really is. This is the third, notice, root of x squared. That's what this really looks like. And again, we have to put a restriction on x because it's not a differentiable everywhere, right? So we would have a problem there at 0. Okay, so that is a problem that we would run into. Now, next one, okay, so for this would have been t, and this is, notice, the 2/5, so that's now my exponent. I'm going to remove these just so that I have space for myself to be able to write it. So this is f, okay, so now the derivative of this is going to be 2/5 t and 2/5 minus 1. That's what we're doing. So 2/5 minus 1, which is 2/5 minus 5/5, right? If you're finding a common denominator there, so this is going to be -3/5. And again, you can rewrite this as a radical if you like, and because the exponent is negative, you can bring it down to the denominator. So I'll leave that to you. So that's what we have there. Now, right here, we do have our radical in the denominator. So this is the same thing as saying y negative 2 over 5. That is exactly the same thing, just by exponent rules. And now the derivative of this, so g of y, is equal to negative 2 over 5 y, and negative 2 over 5 minus 1 is going to be, I guess, negative 7 over 5. And again, you can bring that negative exponent down to the denominator if you like. You kind of have to a little bit worry about making sure, y is not going to be, definitely not 0. You can check if it's a problem for anything else. But that's how you would take the derivative. So all of these that we had in here were basically all of these rules. So I just went one by all of these rules. What happens when it's a constant? Okay, what happens when we have this? What happens when it's negative? What happens when we're talking about radicals? What happens if it's a little bit more than a radical, because it's also n is some number, okay, and so on and so on. So this is what we have. Now, what I will also mention to students, so something that is not always very commonly thought of, because we're so used to having the exponents being rational, don't forget that you can have rationality and the exponents to be written as decimal numbers. So for instance, if you had something like this, if you had fx, which is equal to, say if it was x to the 1.7, the same result still applies. Meaning that if you wanted to take the derivative, and this is indeed a decimal, then this would just simply be taking the 1.7 to the front, and then x, and then 1.7 minus 1, which is just 1.7x to the 0.7. And there's your derivative. Now, you might say, well, that's kind of weird because this is a decimal. It doesn't matter if it's a decimal. You can still take these decimals, and I mean, technically, this is the same thing as 17 over 10 if you wanted to rewrite it and put it as a fraction, if you really wanted to go that way. But clearly, having the exponent 1.7 still works just fine. So don't be afraid with any exponent. It doesn't matter if the exponent is a fraction. It doesn't matter if it's decimal. Okay, it doesn't matter what it is. It is always the derivative is you take the exponent, you bring it to the front, and you subtract 1. So that is something that I really want you to know as students as you carry on, because it's a nice skill to have that you can apply it comfortably to all of these. So that's a side note for those who've gotten to this point of the video, which I think it's going to be useful for you as a student if you're studying calculus, because it's going to make you comfortable. Now, the next set of examples, so within here, so what I want you to see is that this one seems very simple, right? But it is the application of having a constant multiplying a function, right? So in this case, the function is just x cubed. So it's a constant multiplying a power function. So what we say is, in terms of the derivative, so this would have been h, this means it is the constant multiplied by the derivative of the function, which is just 3x squared. And now you can see that the 3 and the 3 you can multiply, so this is going to be just 9x squared. That's the actual derivative. So that's this rule right here that we are applying. Now I'm going to be applying the addition and subtraction rule. So that one is the next one that you see in here. So that's for this. Notice that I have now an addition and a subtraction. So really, this is composed of 3 terms. So you can think of this as basically having 3 functions. The negative 4.9 t squared is one function, plus t minus 10. So the t is another function, and then the minus 10 is another function. And now we're just applying the summation and then the difference of these. So you can do them one at a time. So for instance, the derivative of this, which I'm going to write there towards the bottom, this would have been the derivative of d, is equal to, so now we take the negative 4.9, so notice I have a constant there in front, times the 2, which is going to be negative, I guess is going to be 9.8. This is going to be t, I'm subtracting 1, so that's going to be just that. Plus, because it's the summation, so I can now take the derivative of t, that's just 1, and then take the derivative of the constant minus the, so this is really 0, so this would just simply fall off. And that is my overall derivative of that function. All right. Now, the next item is product of two functions. So here's one function, and it is multiplying another function. Again, sure, people might say, I can bring this inside so I can expand this out. That way I don't have to worry about thinking about the product. Fine, okay? However, this is not always feasible, and it's not always easy and nice to do. And you'll see that when we get to this challenge one, in terms of multiplying through, what if you have radicals? What if you have something else? So it is still worth your time to be able to understand the product rule. So the product rule says that you're going to take the first function, you're going to take its derivative. So that's going to be, in this case, 36, because it's 12 times 3, x squared. That's the derivative of the first one, multiplied by just the second function on its own, without taking the derivative, plus the first function, so 12x cubed, you do nothing to it, and now you take the derivative of the second one, which is going to be negative 1 plus 5, and then x to the 4. And now, sure, if you really want to, you can bring this inside over here. You can bring this inside over here. So you can distribute this across. You can collect like terms if there are any, and simplify as needed. But that is the application of the product. Now, the last example, which I have here for you, is this one right here. And this is a composition. Now, why is it a composition? It is a composition because I have this function inside the radical. So really, what I have is, if I would draw this out, okay, I'm going to just sketch this, just so that I don't take too much time. What is happening here is, you have your input. It is being fed into this function, 2x plus 4. So that is right there what I highlighted. It is being thrown out, so this is a new output here that I have. And now it is being put into another function, and now this function turns out to be the third root, okay, of that, output right there, which is the 2x plus 4. Okay, I'll put a little dot here. And then that results in, and I guess I used the t there, so let me just change this. This should have been a t. All right, that's because of that. But that's exactly what the meaning here is. Okay, so this is what we are dealing with for this particular function. So it is a composition. So by composition, what it means that I have to take, first I'm going to rewrite it for myself. I'm going to write it like this. 2t plus 4, 1 over 3. And now I'm going to take the derivative. So first, you take the derivative of the second function. So that would be 1/3 of 2t plus 4, 1/3 minus 1, which is going to be negative 2 over 3. And then you multiply it by whatever is inside of those brackets. So in that case, this one is easy because the derivative is just 2. Now, that 2, of course, I can bring it in front, okay, with that 1 over 3. and then I am done. But that is the actual derivative of this function. And those are all the different rules that you had. If you understood all of these, and if you're capable of doing these, then great. You know, you're kind of on your way. My focus, as I would present this to any student, is to show all these rules, give you as many examples as I can, so that you internalize the process. And once that's done, then we can start applying it, because obviously calculus is used. So all these derivatives, they are used in certain applications to help us, okay, with various functions to be able to do certain things. Here is the last example, the ultimate challenge that I have for you. And I would encourage you to try to see if you can do this, because it's a combination of everything. So I'm going to just do it in kind of one whole. So what I notice is I have two monstrous functions. So I have a quotient here that I'm dealing with. So I'm going to have to try to apply the quotient rule. So now let me say that this is my f1 of x, and this is divided by f2 of x. Now by the quotient rule, this means that I have to take the derivative of the first, multiply it by the second, subtract, leave the first function, multiply it by the derivative of the second, so the derivative of the second, and then divide, okay, by the second function except it's squared. So I have to do all that work to be able to get the derivative, which clearly is going to look very ugly. So we can do it one by one. Okay. So if I begin, let's take kind of the derivative of the first. So the derivative of the first is a composition, right? It's a composition of the function because I have a 6 and then I have this entire bracket. So what this will be is 6 comes in front. I have this entire junk, which is stuck here. So plus, I'm going to just rewrite the whole thing. This is x squared minus 4. And this is now going to be to the 5. But this has to be multiplied by whatever is inside. And again, whatever's inside is not that pretty. So within here, this thing, okay, inside, so this really is 2 to the x minus 5. This right here is just nothing else but x 2 over 3. So if I'm taking the derivative of those, I will have negative 10 x minus x to the minus 6. That's the first one. Then plus, I will have now the 2 over the 3. Then x. So 2 over 3 minus 1, which is going to be negative 1 over third. And then the derivative of negative 4, which is just 0. So there you go. That's the derivative of the first. That is just this. That's all that I have done. Now I have to multiply it by f2, okay, which is this entire junk. So I would have to multiply this whole thing that I have just done, so this, so you can see this, why this is a challenge, and it's very annoying, but so be it. So now I have to multiply it by that denominator, so 3x, okay, and then take the 4x squared plus 2x. I'm just going to rewrite it there for us. So there you go. That is this, f2. Now all of this has to be now subtract. So I'm going to be subtracting. Take my first function. So I have to now go back in here. So let me go back and just so that I save myself, because I don't want to be rewriting this whole thing again. So I'm going to take this, I'm going to copy it, I'm going to paste it, okay, within here, make it smaller. I don't know how big it should make it, but that is just this. Now I'm going to move over. I need the derivative of my second function, which is the denominator. So now the denominator, notice, it's a product of two functions. And also the second function, it's a composition because there's a radical there. So that one is going to be annoying. So let's try to see if I can knock this one off. I'm going to first start off with that one. So the product of that means that I have 3, which is the derivative of the 3x, multiplied by the actual second. So that's 4x squared plus 2x, right? So the product rule would be take the derivative, multiply it by the second function, plus, now leave the first function alone, and now take the derivative of the second. So that's going to be, because of this, the square root, that's just 1/2 of 4x squared plus 2x. And within here, okay, this is going to be now negative 1/2. And I'm still not done, by the way, right? Because this is, okay, so the derivative of that entire thing, I have to now take the derivative of what's inside, and that's going to be 8x, that's right here, plus 2. And only now am I done. That is monstrous, right? So here is my numerator, and now it's supposed to be multiplying all of this, all of that. That's what I have to do all the way over here. Okay, so I would have to multiply this right there. So now I have done this. And that entire thing has to be now divided by, so my numerator, my denominator, so copy, paste it. Let me clean it up. So let me remove this. And that's supposed to be squared. That's right here. Now, the reason why I gave you this, and I called it a challenge, it's a challenge for a reason, but it's very systematic if you're applying the rules. I've actually applied every rule that I had in one question. So I was thinking of this example for a while, and that is the actual derivative. Now, the problem still would be that we would have to find out where this derivative actually exists, because there are cases that we will have. For example, x equals to 0 just won't work for us. But I'll leave that out of this video, because the idea was, can you apply the rules? And here are the rules that you have. All right, so that completes this monstrous and long video with respect to all of these rules, but I think that these hints that I have given you and this entire summary will help you to get comfortable and will tell you what you need to be comfortable with. You know, how far should you go? How far should you practice the examples so that you understand them? All right, thanks for watching. Hopefully we'll see you in a future video. Bye everybody, happy calculus studying.